Hello and welcome to the third session of machine learning exercises. In exercise 1, we will talk about the ridge regression optimization, and we begin with the OLS optimization in exercise 1a. So think back to your econometrics classes. How did you fit the OLS parameters? You will now derive the formula for fitting the vectors of parameters beta hat OLS or multivariate regression. So let's start with the hold on. Okay, let's start with the population model. So you should all know this equation here. This is the population model from the multivariate OLS regression. So you see that we have multiple betas and multiple features here. I just notated this in sum. You can also write this as a matrix or in matrix form. So this would be the vector of y's is equal to okay, so this is the matrix of the features, and this is the vector of parameters, and this is the vector of residuals. So y goes from y1 to yn. This is an n by 1 metric vector. Then x goes from x11 to x1p exactly, because it's p features, goes to xn1, then xnp. Okay, so this is a n times p matrix. Then let's not forget our parameters. This is a vector from beta 1 to beta p. So it's a p times 1 vector. Epsilon goes from epsilon 1 to epsilon n. So it's a n times 1 vector. Okay, now let's write down our estimation model. So we want to estimate y with the linear model of the features and the parameters. Now, how do we optimize our parameter? We optimize our parameters by minimizing sum of squared residuals. We will do this with our first order conditions. So let's take the derivative, or let's first maybe say that, let's go back and say, what is the SSR? The SSR is the sum 1 to n of the squared residuals. That is equal to this matrix notation. That is equal to the difference in y and our predicted y's. And now let's plug in our estimation model. So this will be y minus x beta times y minus x beta. These are all bold because these are vectors, and a capitalized letter means this is a matrix. Okay, now we want to minimize this with respect to beta, so the vector of our betas. And now let's do this by the first order conditions. So let's take the derivative of the SSR in respect to our betas. That is equal to the derivative of, and let's now multiply this out, so we will have it easier when we take the derivative. Okay, now we've set this all to 0, so we will optimize it. And let's take the derivative. So this will be 0, as there's no beta in this term. So this will be 2. So this, I forgot maybe to say that this little mark here is a transposed sign. So this is the transpose of y. So it's y transpose x here. Plus yeah. So obviously this is x squared beta. So if we take derivative of this squared beta, we will get 2. Then the square matrix of x's, and one beta vector remains. So now, hope I didn't make a mistake, but we know that x transpose x is positive definite, and therefore invertible. So now we can take this term to the other side and then divide by 2x transpose x. So this will lead us to our optimal beta. So this our optimal vector of estimators, which is then x transpose x to the power of -1, then -1 x transpose y. Okay, so this is the solution of the first exercise 1a. And now if you want a more detailed explanation of this, maybe go back to your econometrics classes or your files from the econometrics classes. Or if that doesn't help, you can also post your questions in the DigiCampus forums.